In this video, I'm mainly going to build this handheld force feedback controller, which is based on an existing design and was modified to use a MyActuator CAN bus motor. The same CAN bus protocol is also used in the motors of this joystick. You might remember from a different video. Back in the day, the OpenFF board did not support the MyActuator protocol yet, so instead this joystick has been modified with ODrive Pros instead. Now I want to actually implement official support for the MyActuator CAN bus motor drivers, mainly also for these smaller L-series motors, which open up some very interesting applications for handheld force feedback systems. Now, to connect the motor to the OpenFF board, we had to modify the JST cable, which was supplied with it slightly. It came with one which has the JST header on both sides, but of course we will need to power it with some kind of external power source and need to connect the CAN bus to the OpenFF board. To the OpenFF board, you only need to connect the CAN high and CAN low pins, where I have crimped some pin header connectors to. And on the motor itself, you can also see the pins marked CAN high and CAN low. CAN high is the yellow cable, CAN low the green cable. And you also need to set the CAN bus termination jumper, which switches a 120 ohm resistor across the CAN pins. This is basically all you need. So I've already turned on the motor and now I can connect the OpenFF board. The power of the motor is connected to this boost converter because the motor needs 12 volt and later in the build we want to power this motor from 5 volt. Now that the OpenFF board is connected, we can select the correct motor driver on the Access tab, which is the RMD MyActuator in this case. Then we get the RMD MyActuator tab. It will detect the model, which is the L5005 The most important setting is to set the CAN ID and CAN speed correctly. The CAN ID is also set to 1, exactly the same as in the motor itself. And the CAN speed is also set to 1000K or 1M. Here it is already responding with force. Because this motor expects a current value for torque, you also need to enter the torque range so that forces are properly scaled and do not exceed the capabilities of the motor at maximum torque. For the small motor application, I'm selecting only 2 amps, but depending on the motor and power supply, it could of course be something completely different. This 2 amp setting means that when I set the power to 100% and turn the motor into the end stop, the OpenFF board will send a value of 2 amps as the current set point, which you can see here and also in the graph. At the time of this video, unfortunately, there are a few issues with the CAN bus protocol, and there are 2 ways of getting data from this motor, like the encoder position and status. Either the motor sends a periodic report, which can be enabled, or you request it actively and the motor will reply to a command request. At this time, unfortunately, the maximum update rate of periodic position reporting by the motor itself is only 100 Hz and only for one report at a time, and it also disables all other replies such as status messages. Therefore, I have currently implemented 2 modes. By default, it uses the periodic reporting of the motor itself, which is more efficient, but as I said, has a fixed update rate of 100 Hz for the encoder position. Also, an active request mode can be used instead, which polls for status and position values actively. Then at every torque command, the motor will also send back a status message. And the status message contains a low resolution 1 degree position value and speed estimation. This is also now used to interpolate the position to get a higher update rate. This of course leads to a significantly less accurate position and higher jitter, but much faster update rates depending on the application. If MyActuator updates the communication protocol with a future firmware and allows us to read the actual encoder resolution and uses higher update rate position reports or allows multiple periodic reports with different time steps, the quality could be improved significantly. But at this time, that's likely the best we can do with this. Now let's actually start the main build of this video and finally make the controller. This is not actually my design, it was designed by Bender and he shared the project files with me so I can do the required modifications for the parts which are different in my version compared to his. I will of course link the original project in the description. Of course, one of the modifications is the motor itself. Originally he would have used a different motor with a separate motor driver in the base, which is not required now, and a separate encoder behind the motor. Well, this is all integrated in this motor, so I just had to design a plate for this motor which mounts to the original screw locations. I tried to keep all the screw locations and mating surfaces of the components which I had to modify exactly the same, so it is still possible to mix and match between these components and the original ones depending on the used parts. Another change was the potentiometer. Originally these trim pods were supposed to be used, but I find that they are a little bit scratchy and I mean they don't really feel nice. They have a lot of friction, so instead I want to use this Alps potentiometer, which I still had around, and this is extremely smooth and feels much better. For this the trigger had to be modified slightly with this D-slot. The buttons are still 10mm ones, but I decided to use panel mount buttons instead of these like standard clicky switches. And originally an Adafruit PCB was supposed to be in this location, which I do not have. So I am using these buttons, and for this I also had to extend this piece slightly so that the buttons have enough space behind the panel and do not collide with the shell itself. So the first thing I will do is mount the motor itself. This motor uses M2.5 screws, which is a bit odd because all the other ones, also the threads on the front are 3mm. Now I realized that for this button I will have to snap off these pillars, which usually would hold a little bar for these buttons. I left them in this design so it's still compatible, but it's also easy to remove. Can just snap them off. I'm going to solder the buttons later when they are all mounted, so I can just do a loop for the ground. I might have to remove these. For this one, for the joystick, I will need to remove these pins. They have to be desoldered. Some of these sets come without the pins. The ones I bought had them already pre-soldered, but they would interfere with the buttons in this case. So I'm quickly going to remove them. Oh, okay, that broke off. Doesn't matter. I can fix that. Because this one pillar cracked, I had to add a little bit of glue and wait until it dries. It doesn't really matter, 3 are more than enough. The lower 2 ones are cut off a little bit, so there is space for the joystick itself, which makes them a bit more fragile and prone to breaking. This also broke off while removing the supports, so I added some glue to it. For now, because I already printed this multiple times, I will leave it like it is and see if it holds up. So for the buttons and the joystick, we make the connections very simple. The buttons just need to be connected between ground and a digital input on the OpenFF board. And we have 8 of these inputs on the digital header. And on this board we have 6 buttons, plus 1 inside the joystick for pushing down, and 1 on the side handle, so we are using all 8 inputs. And for the joystick we additionally need 3.3 volts and 2 analog pins, which are on the analog header. Now for the other side of the buttons, we need to solder some wires to them for the digital inputs, and I already prepared some wires in about the correct length. And this last one is going to be the 3.3 volt connection. On this potentiometer it is labeled 5 volt, but that's because it's an Arduino module and previously most Arduinos were 5 volt. And for the trigger potentiometer, I am bending the legs outside a little bit and these ones in, so it can slide inside this section of the left shell. Now for the trigger assembly we are going to need the trigger itself, a bearing, the bearing mount, a spacer plate and the tension arm, which will provide some spring feedback for the potentiometer with a rubber band. I had to do a little bit more sanding on all sections and find a suitable rubber band. I initially wanted to use an actual metal spring. Problem is this section would interfere with the spring and this would not fit very good. Instead, with this rubber band it should be fine. And with this screw being screwed in completely, it should also go over the screw. Well, it's still a little bit too close, but it is not scratching anymore. So this should be fine. And I think I will do a full assembly and test it first before I think about any improvements I could make to the model. Now it's time to solder the wires to the OpenFF board. This is the one I used for testing. But of course, if you put it in front and would mount the shell to it, you can easily say that the headers would interfere and you could not connect anything to it. So I will have to use a fresh board and solder the wires directly to it. So the first thing I'm going to connect to this board is the CAN bus for the motor. On this one you can see that there is a jumper set on the leftmost pair of pins, which is for the CAN termination resistor, which must be connected. So on this board, while it does not have the headers, we will still need to bridge these two pads. And for this I'm going to use this bent, I think it was resistor legs or something. For the motor I'm using this little extension piece. So to make this easier, I'm going to solder it from the back of the board. The yellow one is the CAN H. Next I'm going to do the button plate with the joystick and the front buttons, because that's the largest amount of wires I have to do. First is our ground connection, and this will go to the one of the ground pins from the digital header. We are going to use all 8 of the digital inputs and 3 of the analog ones. Next is the trigger, which I'm going to connect to the third analog input, and of course 3.3 volt and ground again. And lastly we have the side button. So to power this motor I'm going to use a boost converter, which will step up the voltage from 5 volt to 12 volt, which this motor needs. Of course this motor would need more than the 2.5 watts a USB port can safely provide, so I will need to limit the maximum torque significantly in the software. So when closing the two halves of the shell, I have to be very careful with the wires and get them behind these pillars, so they are not caught between the screws and these sides. While attempting to mount the board, I noticed that on the original the wall is slightly too thick. So I did a quick modification and printed it again, so it actually fits in nicely. The interface for the motor driver goes in where the other microcontroller would have been in the original design. These are a little bit longer, so they should fit through the shell and the OpenFF board. Back here I am going to use longer 20mm screws. Of course, holding the motor in this state just by hand is a little bit difficult, so I need to mount a little wheel to it to extend the motor and make it a bit more ergonomic. For this I have designed this adapter, which mounts to the RMD motor and would allow you to either use the original wheel piece of this design or a slightly different one, which also features a little piece with a bearing you can put your finger in. And this is what I would like to try and see if it makes it a little bit easier to use. Because this controller is now a standard direct input compatible device, it works with almost every game that supports wheels or classic gamepads.
Two right, opens 4, 70, 2 left, long tightens, 60.
Even without force feedback support, like in Revolt, it is still very usable with the idle spring effect. And lastly, I want to thank Bender for the controller design and my Patreon and Discord community for supporting my projects. Check out the links in the description for sources and more information.